So today I'm going to present comparing one and binary class SVM-based software defect predictors. And the agenda contains the problem statement, its relevance, and our contribution in one class classification especially. So first, what is SDP, the software defect prediction? We're going to say that in the P in SDP stands for prediction, and it's used as classifying software as being defective or non-defective. And in this regard, we're gonna see that SDP works on different levels of abstraction. Namely, it can be on the line of code level, or it can be on a directory or project level, where the annotation as buggy or defective is placed. So mainly what we are focusing on is the pre-processing of the text or the code itself. So the machine learning algorithms usually cannot process just raw chunks of code. So we need NLP tools for transforming the code into a vector representation or extracting aggregated features that we can talk a little bit later about. And as I said, the input of these machine learning classifiers is this processed information, and the output consists of understanding if that software is defective or non-defective. So this is how a pipeline should look like. Mostly it is about taking the code, and we, as programmers, have languages of, like, say here is Java. So we have to relation every keyword in here to the others, construct an abstract syntax tree or something like this, and see how the variables are related to each other and what they affect and how the functions are used. So mostly it's gonna be getting these words into some kind of representation that can be uniform and processed by NLP, by the ML models. So features, as I said, are basically based on some kind of metrics. Like for the abstract syntax tree, we can consider some relationships. The code can be considered as a graph, and the number of nodes, the complexity, I mean, the connectivity of each node or other static features can be deducted from these processed code, or anything that relates to the quantity of code that has been written from a version of another of a software. And these kind of features can be used to further analyze and understand the context of the project we're in. Mainly what we're focusing on is that we have larger software development nowadays, and the industry is always growing. And there are a lot of problems arising from the fact that code might not have been well written in the past, and we may be facing the consequences now. However, when introducing AI to software defect prediction in IDEs and software development tools, we may be able to constantly check for defects and ensure quality before it reaches production and creates critical errors. So this is mainly why we are focusing on research in software defect prediction. Here are a few examples of what I mean by legacy code. Like, there are problems when we are talking about trying to refactor code or trying to understand where the bug is, and this takes a lot of investigation and man hours into the projects. And also there may be some kind of code that hasn't been written for some applications like parallel or concurrent programming, and when it comes to that point, without paying the appropriate attention to these matters, it can ruin the project. So the methodology of developing nowadays is mostly agile, and in this regard, we are having a lot of team members, and there must be a lot of communication performed in order to properly understand the client requirements. So always there can be the problem of not being able to get the whole information and the whole picture. So there may be features introduced in the project without needing them actually. So this leads us to the classification of defects, or a few of them. And yeah, we have here some usual causes of defects and how they may manifest in our code. And mostly this leads us to the difficulty of the domain, especially in software. Now that we have QA testing and so on, we usually do not have defects in production or in it's more common to write well-written code. I mean, to have defects, not have bugs, but this thing that we are looking actually for bugs in order to classify them, we don't have many samples to use in supervised learning machine learning models. So it's this is why is the main cause why supervised models may underperform. And also in order to properly understand the bugs, as we've seen that there are a lot of types, we may need a lot of context of the software project that we have. So in order to compensate for these, especially class imbalance problems, there are some statistical approaches like rebalancing, generating more data, or oversampling defects in order to create more close proportions of the two defective and non-defective instances. However, we are not going to be able to get much improvement for software defect prediction for supervised learnings, and we are focusing more on unsupervised learning formulations that we're going to talk next about. So here we have two main types of classification. The one class classification is unsupervised paradigm, and it's more appropriate for SDP because it can use only one type of class, say the majority, the non-defective classes, without ever seeing annotations of, without ever seeing data of defective software. So this is the main advantage, that we can use only one type of the two classes, and we don't have to annotate first, and we don't have to search for bugs. And the main approach is using, in our paper, SVM and one class SVM. The SVM usually, as we see in the left side of this image, takes several classes, several instances. And what it does is that it creates hyperplanes between the data in order to classify them. However, the one class SVM, as I said, doesn't have to classify between instances, and what it does is that it takes the majority class and creates a hypersphere around them that encapsulates all the instances or the inliers, and everything that's outside, it's considered an outlier. So next, what is the SVM plus and minus is that we are going to have different models of SVM trained on defects and non-defects. So this leads us to the research questions. The first one refers to the effectiveness of one class SVM, especially trained on positive or negative data, yeah. And the second one refers to the one class SVM performance compared to the classical SVM supervised learning model. So we are working with Calcite. It's a software application that it's in online. You can search it yourself and you can find it. It's from Apache. It has 16 versions of the software that has different defective rates. As you can see, that it decreases as the software gets to the highest version. And here we have the imbalanced data that we are talking about, because there are the green ones are the defective instances, and there are very few of them. And this is the main reason why we're using unsupervised learning, because we don't have an equal proportion of the defective and non-defective instances. So again, for software faults or defects, we are going to use the plus notation. And for non-defective instances, we're going to use the minus. This is because we're going to use the ON class SVM plus and minus in the notations in the next slides. And also, we have the experiments that we are going to talk about. The first one refers to training on consecutive versions, like 0 and 1, 1 and 2, training on 2 and testing on 3, and so on. And the second experiment refers to using all the versions from the first one, from 0 to the kth, and testing on the k plus first version. Okay, so these are the performance metrics. We're going to mostly focus on probability of detection, which is also related to recall, and the false alarm ratio, which is also an important factor in software defect prediction, as this one mostly annoys the programmer if there are too many false positives, and a lot of time may be wasted if we check unnecessary chunks of code. Usually the false alarm ratio has to be lowered, and the other metrics have to be maximized in order to get perfect predictions. So here's the first table. It's a large one. We don't have to mind reading it all, but basically what we have is the experiments of training on version 0 and testing of version 1 here for the one class SVM plus and minus compared. Here are the confusion matrix. Here's the confusion matrix, and the yellowish cells in here are represent the better performance of the models. So this is similar to the next table that we have at the experiment E2, and here we see that it follows the same structure, but the versions the model has been trained on are from 0 to the k, tested on k plus 1 for first version. Okay, so overall what we have to focus is that we aggregated the results, and we have here the information about the experiments, and the relevance of this table consists of the fact that we have the model that had the more metrics favorable to its performance got a win, and a loss was considered when the one class SVM plus was outperformed by one class SVM minus with more metrics on its side. And we can see that the one class SVM performs a little bit better on the first experiment, but the second experiment is where the margin is a little bit wider, and we can rely more on one class SVM compared to the one class SVM minus. Another advantage is that the first model is being trained faster than the second and on less data, as it's trained only on defects. And mostly this is our answer to research question 1 regarding the comparative performance of the two one class SVM models. And for the second question regarding the performance of one class SVM compared to the binary SVM, we see here, as we discussed, the pod and far metrics. In regards of the pod, we don't have a clear advantage of one class SVM over the other, the SVC, the support vector classifier. However, the thing is that in terms of far, we have less false positives for the supervised model, And this may be because it saw all the data, and the one class SVM plus saw only the defects. So the first factor may be that the data was not enough. I mean, there weren't enough data instances. And the second is that it's still an supervised model, and may have had some problems in here. Another thing to consider is that we have two hypotheses, one of random guessing that basically returns a 50-50 chance. I mean, not a 50-50, a chance of returning a positive, a defect in accordance to the defective rate R, or a non-defect. So this is the confusion matrix for the random guessing hypothesis that we have with the dataset of n instances. And the 0R hypothesis, that means it would return always a non-defective instance. As we see, we have 0 and 0 here. It won't return any defects. So it's like a classifier that's randomly simply just returns 0. And we see here that we do have improvements compared to them in terms of one class SVM. And we do have a significant improvement in terms of POD. However, the specificity is with minus here, because as we saw previously, there were some problems with the false alarm rate, and it may be a little bit worse than I'm guessing in some cases. However, it is significantly better overall. So it passes this hypothesis, and this is our answer to the research question 2. Then we have the conclusion. So all in all, it is difficult to understand the software defect prediction for bug annotated software like Calcite, because the annotation consists only on having a true or false label, like if there were or not defects. But as we saw previously and discussed, there are many types of defects, some of which may be very hard to pinpoint in code, like the code is functioning properly, but the requirement got misunderstood or something like this. And we believe that we should have better annotated, or the defects should have more information, more attributes like the severity, the cause, and nature of them, in order to properly have well-functioning software. And for future enhancements, we may verify our findings on several other Apache software systems, and maybe also try to perform other experiments, like train on a whole project and test on the others, and perform an in-depth analysis with more metrics, and that may be more relevant to these class imbalance problems and overall in the software defect prediction literature. Okay, so thank you for your attention. I'm here to answer your questions.